Hi, welcome to Mr. Carroll's classroom. Today we're going to take a look at solving radical equations, so let's check them out. Okay, so whenever we're solving any types of equations in mathematics, essentially what you want to find is the most complicated operation in that equation, and then isolate it in order to eliminate it. So let's go ahead and take a look at those steps. So number one is we want to isolate that complicated operation on one side of the equation, and then we can use the inverse operation on both sides in order to remove it. Now, if you have multiple complicated operations, then simply isolate one of them and then remove it, and then go ahead and isolate the next one and then remove it, and so on and so forth. Okay, so a couple of examples here. So here are some example equations, and let's just identify the complicated pieces here. So we have a binomial squared. Here we've got a radical, and here we've got an exponential. So first step is going to be to manipulate your equation in order to get that complicated operation on one side, as you can see we did here. And then we can take the inverse operation of both sides in order to cancel that complicated operation out. And then we can continue on to solve for whatever we're solving for. Okay? All right, so let's take a look at what the inverse operations of radicals look like. And we're going to talk about it in terms of square root, then cube root, and then we're going to talk about it generically as any nth root. Okay, and what I want you to really, or what I want to be really clear about is that with a square root, it has an index of 2. And actually, let's go ahead and bring this up. This is what it looks like, right? So here's the square root of x. Well, technically, it has an index right here of 2. It's just that we don't typically write that, or at least if it's not written, then it's inferred that we're talking about the square root, which has the index of 2. But anyways, what I want to be clear about is that anything that we do with a square root, it's really going to be the same thing for any index or any even numbered index. So an index of 2, like this one, a square root, or an index of 4, 6, 8, whatever. This is going to apply to all of them. And then a cube root, it's going to apply to all of the odd numbered indexes. Okay? Anyways, so the square root can be written as the radical symbol right here, so the square root of x, or it can be written as x to the 1/2 power. We will use both. But ultimately, if I want to take the inverse operation of that, then the inverse operation of a square root or something to the 1/2 power is squaring that. Okay, so this will cancel out the square root. And it's actually really clear to see it right here. If I have x to the 1/2 to the second power, then I would multiply these exponents to get 2/2, which is really just 1. And that's the reason why squaring something is the inverse operation of something to the 1/2 power or the square root. Okay, but anyways, ultimately that whatever's inside there will pop out, and we have kind of quote unquote undone our complicated operation. Now, of course, we can't actually just do this to an expression, but with an equation, we can do that as long as we do it to both sides. Okay, so let's take a look at the cubed root. So cube root has an index of 3, or it's x to the 1/3 power, and so the inverse operation is going to be taking that to the 3rd power, in which case, just like before, the inside, whatever is on the inside of here, it could be something complicated. In this case, I just have x, but anyway, that is going to pop out of there. And then with the nth root, just generically speaking here, the nth root of x, or x to the 1/n power, we would take both sides to the power of n, all right, in order to undo that operation. And of course, the inside will pop out. Now, it is worth noting here that whenever we're starting with a square root, a cubed root, or any nth root, all of these, actually, I should say the evens, are restricted to the positive numbers. So, for example, if you looked at the graph of the square root of x, it goes off into the positive quadrant. And that's because we restrict that to, we don't allow negatives. And so because that's the case, like this is not going to be like plus or minus x. which is not true when we go the opposite direction. Okay, so all of these just work as you would think they would work. However, it is worth just taking a look at here. If we were going in the opposite direction, you do end up seeing these pluses or minuses. So I want to show you what that looks like in case you've never seen that before. So if I'm starting not with the square root of x, but if I'm starting with x squared, and I want to undo that, right? Then what's the opposite operation? Well, the square root is the opposite operation. And what's the opposite of x cubed? Well, the cubed root. What's the opposite of, or the inverse of x to the nth power? Well, the nth roots, right? And you would think that, okay, that's fine. The x's just pop out. But that's only true, really, for the odd indexed operations here. Okay, it is actually not true for the evens. Okay, with the evens, we actually have to add this plus or minus. And the reason why that is, and I'm not going to go into great detail here, but I do encourage you if you're interested in kind of researching this a little bit. But I want you to think about like what we're starting with here, this x squared. The x squared is a parabola that is in both the second and first quadrant. In other words, it has negatives for the x's, so it does allow for x's in this domain. And when we twist this 90 degrees or take the inverse of that, just taking the square root only gives you half of that parabola. But we really need both of them, right? So we have to add in the plus and the minus. And that's why we get this plus or minus out of here, because the square root doesn't allow for the negatives, but then we're going to be missing those. So that's why we end up having to put in the minus as well. Okay. So ultimately, though, what is the rule? If you ever have an x squared or x to the fourth or x to the sixth, x to the any even power, and then you have to take the square root or the fourth root or the sixth root, any even indexed root, then you should always take plus or minus. Anything that's odd, you do not have to worry about it because there were no restrictions on odds. So anyways, again, if you want more detailed information on that, then I encourage you to look it up. And real quick, another way of looking at this is if I have x squared is equal to 1, well, what could x be? Well, x could be 1 times 1 is equal to 1, but it also could have been negative 1 times negative 1 is equal to 1. Those are both valid answers, and that is a part of the reason why we have plus or minus. Now, over here on the right-hand side, if I have the square root of x is equal to 1, well, what can x be? Well, it could be 1, right? Because the square root of 1 is just 1. But it couldn't be negative 1, because what is the square root of negative 1? Well, it's definitely not positive 1. The square root of negative 1 is actually defined as I. So we would end up in this complex number system. Now, again, the square root of x does not allow for, in order for it to be a function anyways, it does not allow for those complex numbers. So we try to stick only to the real numbers. So that's another reason why this is not plus or minus. This just gives you the plus version. However, if you started with the x squared, you do get the plus or minus. And that's showing right up here. If I start with the square root of x, then I'm just end up with the positive version. If I start with x squared, then I end up with the positive and the negative version. So now there's a lot to talk about there. Again, I encourage you to look that up if you're really interested. And by the way, it's not all like very clear either. People argue, and it is debatable. Okay, so anyways, whatever. Let's go ahead and continue, and let's show some examples. We're not actually going to take those. We won't end up with any plus or minuses in these particular examples, but once we start learning about inverses, then we definitely will. Okay. So, anyways, let's go ahead, and I do have quite a few examples here because these can take many different forms, and I want to cover them all. And then one thing you should note, though, is that with all radicals, you need to check all of your solutions because you do end up with quite a few extraneous solutions. We'll see if we end up with any of them in these examples. Okay, all right, so let's go ahead. We have our first problem here. And so this one might look a little bit complicated at first, but it's really not. You might notice, whoops, hang on one second. get my pencil here. You might be thinking, oh, how do I combine these two, right? How do I take this radical and minus the other radical? Well, let's remember our steps. We have something complicated. Actually, we have two things complicated, but let's just concentrate on one, right? We're going to isolate that one thing, and then we're going to go ahead and get rid of it. Now, in this case, this is actually an easy problem. You'll see here in a second. So I'm going to subtract this radical over to the other side. So I end up with 2x minus 1 on the left is equal to the square root of x plus 5 on the right. And now I'm going to go ahead and take the inverse operation of square root, which is squared. And notice that both of these are going to pop out. We're very lucky there. So 2x minus 1 is equal to x plus 5. And I can just solve for x, so subtract x from both sides. So 2x minus x is equal to x on the left, and then I'm going to add 1 to this side, so x is equal to 6. Now, I do want to go ahead and check this because, again, we do end up with a lot of extraneous solutions with radical equations. So let's go ahead and check this real quick. All right, so if x is 6, then that means I have 2 times 6 is 12 minus 1 is 11. So that's the square root of 11. Minus, and actually maybe I should write this up here, the square root of 11 on top right here. And then I have minus x plus 5, so that is 6 plus 5, which is also the square root of 11. So the square root of 11 minus the square root of 11, well, anything minus itself is equal to 0, so we are all good. Okay, so this checks out. All right, let's go to the next problem. All right, so in this example, I have, let's see here, 2x plus 8 to the 1/2, which, by the way, anything to the 1/2 is the same thing as the square root. I'm going to go ahead and leave it as in the 1/2 notation, just so we can get used to that. But anyway, plus 16 is equal to 18. Let's go ahead and isolate this thing. So I'm going to isolate the complicated part. So that's 2x plus 8 to the 1/2 is equal to, I'm going to subtract 16 from both sides. So 18 minus 16 is equal to 2. Now that this is isolated, I'm going to take the inverse operation. So the inverse operation of something to the 1/2 is that thing squared. So I have to do it to both sides. And so, of course, these are going to cancel out, just dropping out the 2x plus 8 is equal to 2 squared, which is 4. And now I can go ahead and solve. So I'm going to subtract 8 from both sides. So that's 2x is equal to 4 minus 8, which is negative 4. And then divide both sides by 2. So x is equal to negative 2. Let's go ahead and check this. So if x is equal to negative 2, well, that's 2 times negative 2 here is equal to negative 4. Plus 8 is positive 4. So that's 4 to the 1/2, or the square root of 4, which is equal to 2. And then that it means this whole thing evaluates to 2 plus 16, which is equal to 18. So yes, we are all good. This does check out. One thing I want to mention is that sometimes this is easy to solve for if you have it on your calculator. If you were to take it at this step right here, this isolation step, this is technically, actually, let me grab this color here. This is, what do I have? I have 2x plus 8 to the 1/2 on the left, which is the square root of 2x plus 8. And that's equal to 2 squared, which is 4. So technically speaking, if you were to graph both sides of these as separate equations on your calculator, the left-hand side is going to be, it's going to look like some, a square root. So it's going to be something like this. And if you graphed this side, y is equal to 4, then it's going to be some kind of line like this. And where's the actual answer to this lie? Well, in this case, it's where they intersect. All right, and this is totally off because this is getting shifted over to the left and whatnot. Where these actually intersect, if you were to graph these, is actually at x is equal to negative 2. So this whole thing needs to shift over. But regardless, once you have this thing isolated, you can just say y is equal to that, and then y is equal to whatever's on the right-hand side. And if you look at where they intersect, you can get your calculator to tell you what that x value is. So anyways, a little shortcut there if you have your calculator handy. And I would encourage you actually to try that out to see how it works, just in case it's a method you want to use in the future. All right, so let's go to the next problem. So here we go. Here we have a cubed root. So the only thing that's really going to change here is we're going to end up taking, this thing cubed once we isolate it. We have to isolate it first. So let's go ahead and do that. All right, so I'm going to go ahead and I'm going to subtract 4 from both sides to isolate this. So I have the cubed root of x minus 1 on the left is equal to 2 minus 4, which is negative 2. And straight away you might be thinking, well, how could this ever be negative 2? Well, it is okay. Now, if it was a square root or a fourth root or a fifth root, you couldn't have a negative over here, so you wouldn't have a real solution. But this is a cubed root, right? And cubes do allow for negative numbers. Let me just show you an example. The cube root of negative 8. Well, the cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is equal to negative 8. So that is equal to negative 2. So anything with an odd index, any radical with an odd index is totally okay. Okay, so let's go ahead and continue on here. So we need to take the inverse operation of something, a cubed root, which is cubed. So we're going to cube both sides. All right, and so these are going to cancel out these operations, just leaving us with what's inside, which is x minus 1. Is equal to negative 2 cubed. Well, we just actually said what negative 2 times negative 2 times negative 2 is. Well, that's negative 8. And let's solve for x. So add 1 to both sides, which means that x is equal to negative 7. Now, before I say this is correct, let's go ahead and check this. It should work because with these odd indices, we really shouldn't end up with extraneous solutions because there's no restrictions there. But let's go ahead and check. So this would be negative 7 here. Minus 1 is negative 8. And the cubed root of negative 8, we just said, is negative 2, right? So this whole thing evaluates to negative 2, which is 4 minus 2, which ends up being 2. And so that is correct. So x is equal to negative 7. All right, let's go to the next one. Okay, so these are going to gradually get a little bit harder. This one is definitely a little bit harder. So the reason why is because we have this x in here, okay? And you're going to see what happens in a second here. So let's go ahead and isolate our complicated piece here. So we're going to say I'm going to add x to the other side. So this is going to be 3x minus 9 is equal to, I'm going to add x. So it's going to be negative 3 plus x. Well, I'm going to put that first. So x minus 3. Just ordering it appropriately. And now I'm ready. I can go ahead and take the both sides squared. And so this side on the left is okay. This is just 3x minus 9. However, on this side, I have x minus 3 squared, which is x minus 3 times x minus 3. So yes, we do have to multiply this out. So we have to double distribute. So when I do double distribute this, this is going to be x squared minus 6x. And then negative 3 times negative 3 is positive 9. And now I'm left with this quadratic. So how do we solve quadratics? Well, let's go ahead and set it equal to 0 and see if we can factor. And if we can't factor, then we'll have to use the quadratic formula. Hopefully it doesn't come to that. So I'm going to go ahead and I'm going to subtract the 3x and then add the 9. So I get 0 is equal to x squared. And then let's see here. I'm subtracting 3x, so that's minus 9x. And then if I'm adding 9, that's plus 18. Good. Okay, I'm just double checking my work here. Let's see here. And so we're going to see if we can go ahead and use guess and check to factor this. So anyways, so I know it's going to be x and x in the front because it's just an x squared here. And now I need two numbers that multiply to positive 18 and two numbers that add to negative 9. So that is going to be negative 6 and negative 3. Negative 6 times negative 3 is positive 18. And then negative 6 plus negative 3 is negative 9. So now I have two things multiplied by each other equal to 0. So I can set each of those equal to 0. So x minus 6 is equal to 0. And x minus 3 is equal to 0. And so now finally I have x is equal to 6 and x is equal to 3. All right, now let's go ahead and check these. Usually with these like quadratics, where we end up with quadratics in here, we usually do end up with some extraneous solutions, and sometimes it's both. Let's go ahead and plug these in and check. Let's plug in 6 first. So anyways, if I plug in 6, we'll do that over here. So that would be the square root of 3 times 6, which is 18, minus 9, which is 9, minus 6 is equal to negative 3. So that means the square root of 9 is 3, minus 6 is equal to negative 3, and 3 minus 6 is negative 3, which is equal to negative 3. So this one works, so x is equal to 6 is all good. Let's do the next one. Let's plug in 3. If I have the square root of, let's put it up here. The square root of 3 times 3 is 9, and 9 minus 9 is 0, minus 3, which x is 3, is equal to negative 3. Well, the square root of 0 is 0. And then, so that's 0 minus 3 is equal to negative 3. And, of course, negative 3 is equal to negative 3. So this checks out as well. I'm a little bit surprised. But, yes, both of these do check out. So we have two solutions here. All right, let's go to our last and final example here. This problem is going to be kind of similar to the one before. And it might look more complicated, but it actually isn't going to be too bad. And you'll see what happens here in a second. So first of all, we have two complicated things. I have two square roots, and one of them is already isolated, this one. So I'm simply just going to go ahead and take the square root of, I'm going to square both sides, and let's see what happens. So when I square both sides, that is going to be x plus 1 all squared is equal to the square root of x plus 3 squared. And so, of course, this is going to pop out here, the x plus 3. So this is just equal to x plus 3 on the right-hand side. However, on the left-hand side, I have the square root of x plus 1 squared. So let's go ahead and do that work over on the side. So we'll do that over here. That is the square root of x plus 1 times the square root of x plus 1. All right, and we're going to go ahead and double distribute. So the square root of x times the square root of x is just x. The square root of x times 1 is the square root of x, or 1 times the square root of x. And then let's go ahead and do this one. So 1 times the square root of x is the square root of x. And 1 times 1 is 1. All right, so let's go ahead and simplify this a little bit further. So this is equal to, this is x plus. So if you have the square root of x plus the square root of x, that's 2 times the square root of x. I have 2 of those plus 1. So there we go. Let's go ahead and move that over. So that is going to be x plus 2 root x plus 1. And now I need to go ahead and isolate again because I still have this complicated piece here, which is that 2 times the square root of x. So it's going to be a little bit lengthy, but let's get through it here. Let me choose a different color. Anyway, so let's go ahead and isolate. So I'm going to subtract 1, and then I'm going to also subtract x. Oh, actually, it's not going to be that bad. So I'm left with the 2 times x on the left-hand side. And when I subtract x, these are going to cancel. X minus x is just 0. And then 3 minus 1, when I move that 1 over, is equal to 2, which means that now I'm going to divide both sides by 2 to isolate that square root of x. So square root of x is equal to 1. And now, kind of got lucky there. Let's go ahead and we're going to square both sides now that radical has been isolated. And so this is going to pop out here, the x, and it's equal to 1 squared, which is just 1. Now let's just go ahead and double check this. That was a lot of work to get there, but let's make sure it works. So the square root of 1 is just 1. So that's 1 plus 1, which is 2. And then on the other side, I have the square root of x, which is 1, plus 3, which is 4. The square root of 4 is 2. So 1 plus 1 is 2 is equal to 2, which was the square root of 4. So yes, this does check out. Okay, you guys, so there you go. There was a lot of different examples there on radical equations, and there are actually a number of other forms as well. Specifically, once you start asking for the inverses of these of radicals, and also their inverse partners, which are quadratics and cubics and quartics and all that kind of stuff. That's where we really start to run into those plus or minus issues, and we'll definitely see those in a future lesson. But there you go. Hopefully you found this lesson helpful, and I hope to see you in the next one. Bye now.